Okay, this is where we somewhat left off last time. We have an absolute center problem under consideration on a network which is embedded on m vertices, and the objective function we have is the maximum of the weighted distances from any point x to all vertices, plus there's an addend associated with each vertex. And the addend, you can interpret that, as I said before, as, for example, the time to get to the nearest hospital from vertex vi, or as a setup time to start, for example, firefighting. And with this, I gave you one property, which is property 1, which said that this minimization is well defined. In other words, there's always a point which will do the job. So there exists a point x bar such that x bar is in n and f of x bar is less than or equal to f of x for all points x in n. There's always a minimizer. The second property has to do with these numbers, which I called alpha ij. What did I call it? Alpha? Is that what we did? Okay. So after this, we decided to define a number, alpha ij, which is equal to I'm going to give you the typically traditionally used one, which is wi times wj, distance between I and j, plus wj times ai plus wi times aj divided by sum of the weights. Is this correct? Because I don't have it in my notes. Okay. The one I prefer is the distance plus ai plus aj, actually ai divided by wi, plus aj divided by wj, the entire thing divided by 1 over wi plus 1 over wj. That's the one I prefer, because of some of the things we will do in a few minutes. Okay? And this is for I less or equal j less or equal n. Okay? For each one. Now, of course, some of the AIs might be 0. In fact, all of them could be 0, in which case you simplify the notation. Also, you might notice that when I is equal to j, the output of that is AI. And the property 2 that I started discussing was the following. F of x is always greater or equal the maximum of these numbers, which I called w of n. So the definition of w of n is the maximum of alpha ij's maximum over all possible pairs. This is true for every x in the network. And as far as I remember, there was no proof for you. So when you begin proving such things, you begin with an arbitrary element x of the network, so that when you say let x be in the network, that's what that stands for. Then whatever statements you can do for that arbitrarily picked one will be true for everybody. Okay? So let x be in N. Then, of course, we know that because the definition of f of x is the maximum of those weighted distances, then f of x is greater or equal wi times dx vi plus ai for every I. Because f of x is the maximum of those terms. So it should be greater or equal each of those terms. So this set of inequalities is equivalent to the following. If I subtract ai from both sides and divide both sides by wi, this is what I've got. F of x minus ai divided by wi. So what I can do is, since this is true for every I 1 up to n, I can pick the ith inequality and the jth inequality and I add them up. When I add them up, I get dx vi plus dx vj on the left side. On the right side, what do I get? I get, well, whatever you see here. F of x minus ai over wi plus f of x minus aj over wj. You get this. And then by triangle inequality, this is less or equal. Actually, dij is less or equal the sum of those two distances. Somebody said a comment? Ataber?
I asked for what that delta equals to.
Triangle inequality. That stands for triangle inequality. All right, so by triangle inequality, which I'm using here, the direct distance going from I to j is no larger than the distance from I to j via x, which is less or equal to the right side you see here, which comes from the upper portion. By the way, that's true for every pair I and j. Because of the symmetry, of course, I less than j, less or equal to j, can be imposed. Okay? So it follows that dij is less than or equal to f of x into 1 over wi plus 1 over wj minus ai over wi plus aj over wj. I'm just rewriting that by removing the term in the middle, and I simply factored f of x out. That's all. And these inequalities give the following. What do they give? They give dij plus the quantity in the parentheses with a negative sign in front. You just add that here, ai over wi plus aj over wj. So I'm simply adding to both sides that quantity, and then I divide the entire thing by 1 over wi plus 1 over wj. And that leaves f of x on the right side. And this, of course, is your alpha ij. So we simply proved that for an arbitrary point x in the network, f of x is bounded below by alpha ij, but this bound is applicable for every possible pair, which means f of x is greater or equal the maximum of them. Yes?
We proved that we can linearize the maximization part of the objective function.
No, we're not really. No, I wasn't trying to linearize it. No. This is not. See, linearity is defined in n-dimensional spaces. Here, you can only say that the function under consideration, if you look at a particular term for fixed I, this function is a linear function of the distance, but not of x. You see, there's a difference. This is a linear function of this thing. So you may view it as a linear function of this sort, where y is a real variable ranging from 0 to whatever it can go up to. Okay? But it's not a linear function of x. So your question, I'm not sure what it refers to, but all I was trying to show here is that f of x is bounded below by this number, which is computable, because dij is a given number. These addends and weights, they are given numbers. So in terms of the problem data, I can simply compute each alpha ij a priori without doing any optimization, okay? And compute the maximum. And that will give me a number. This is going to be some number. And that number will be the smallest I can get for my optimization, for my minimization. Whether or not you can attain that bound is another matter. It turns out that sometimes you do, sometimes you don't. And if the network under consideration is a tree network, you always attain that. But for cyclic networks, sometimes you fail. Nevertheless, it's a good lower bound. Okay? I don't know if I'm answering your question, but okay. So anyway, that's the end of that proof. Yes? Can I? This one? Okay. Oops. Let me give you another property. The weighted diameter of n computed by the maximum of the alpha ij's is supplied by a pair, say S and T, where S could be equal to T, or maybe different. So Wn equals alpha St, and that's going to be equal to some f of x, well, going to, for some x, if and only if the vertices Vs, Vt, and the point x satisfy the following conditions. 1. The direct distance from S to T is equal to the indirect distance via x. Number 2, the weighted distance Ws dx vs plus as is the same as Wt, distance between x and Vt, plus At. And number 3, Wi dx Vi plus Ai is less than or equal to the weighted diameter of the network. This should be true for every I. Different from S and T. Well, why do I worry about such a statement? The reason is the following. Here, property 2 states that f of x is bounded below by this weighted diameter of the network. Now, of course, you question, is there an x which can attain this bound? Of course, if there's an x which can attain the bound, that would be an optimal solution because you cannot get any smaller than the bound. Okay? So, that would, if you somehow ensure under what conditions this f of x will be equal to the lower bound, then of course that would also supply you the solving x, the point that solves the problem. Okay? So, that's why we worry about these things. So, the lower bound is going to be attained by some point x, and I assume the lower bound is defined by some pair S and T. Okay? If and only if the vertices S and T under consideration plus the point under consideration satisfy these things. The first condition simply says that x must be on a shortest path between S and T. Otherwise, that inequality will not hold. Okay? Sorry, that equality will not hold. This is always, DST is always less or equal that, but we want equality, and that's going to be true only if x is on a shortest path between S and T. I'm saying on a shortest path because there may be more than one shortest path between x and T, S and T. Okay, number 2. The weighted distance as computed from point x to vertex S and the weighted distance from point x to vertex T, they are equal. If you remember, we had this jagged line which we used, the piecewise linear function which we used to actually identify local optimum. And in the local optimum, what did we require? We required that two linear pieces must intersect, one coming with a plus slope, the other one coming with a minus slope. In this case, of course, one piece is defined by S, the other one is defined by T. They are in opposite directions, and that's what that says. Okay? So, moving slightly to the left or to the right of x along the path connecting x to either vs or to vt will not make you better. You cannot reduce both of them at the same time. If you reduce one of them, the other one gets larger. Okay? That's the idea. And the last one says, that's not good enough. Then the weighted distance from x to every other vertex must not be larger. In other words, s and t should determine or define the value of f of x. Okay? Because if one of these guys, well, actually we're talking about the weighted diameter. If this inequality does not hold, if it's reversed, then it will be actually the case that f of x will be greater than either of these quantities you see in number 2. Okay, that's the problem. Okay. Now, of course, this is both necessary and sufficient because it's an if and only if condition. But I'm just going to give you the necessity part. You can work on the sufficiency part at home if you wish. Okay? Because it's just, I don't want to bother with everything. So, to prove the necessity, we assume that the first statement is true, and we'll show that the remaining ones should hold. Okay? So under that assumption, let me put parentheses here. Number 3 holds because of the following. Because by assumption w of n is equal to f of x, we assume that, okay? And f of x is certainly greater or equal wi dx vi plus ai for all I. This is from the definition of f. F of x is the maximum of those quantities, so it is greater or equal. But at the same time, f of x is greater or equal wn. So number 3 obviously holds in this case. Okay? To show number 1, which is this one, I'm going to begin with dst plus as over ws plus at over wt divided by 1 over ws plus 1 over wt. How much is this? Alpha st. So, by assumption, f of x is equal to alpha st. Okay? We know, or by assumption. And of course, this will give you dst if you simply multiply both sides by the sum of the reciprocal weights and then subtract the a over w from both sides, we get f of x over ws plus f of x over wt minus AS over WS plus AT over WT. I'm just doing what I did in the proof of property 2, actually, in reverse order. Okay? We're simply doing this, which is equal to f of x minus AS over WS plus f of x minus AT over WT. And now, this one is greater or equal WS dx VS plus AS minus AS. You see why? Because f of x is equal to
X is the minimizer, so we can change it.
yeah, f of x is equal to that, so we're yeah. F of x is greater or equal each of the distance terms, so f of x is greater or equal this term that I wrote down here. And I'm simply copying this over here, okay? This is from the definition of f again, plus, again from the definition, Wt dx Vt plus At minus At over Wt. Now, what does that give you? This gives you, of course, it gives you dx Vs plus dx Vt. This inequality is simply from the definition of f again. This equality is simply a simplification of the expression we have, and this is greater or equal dst. So what did I do? I began with dst. I showed that dst is greater or equal this thing, which is greater or equal dst due to triangle inequality. And of course, because the lower and upper bound are the same, everything is sandwiched, everything holds as equality. So, implying that the inequality over here holds as an equality. So, number one is proved. Actually, all I've got another inequality here, so let's write all inequalities hold as equalities. Okay? Proof number two. Actually, I'm going to make use of the same thing here. Observe that the proof of number one shows that the inequality in the third line is actually an equality. Meaning that f of x is actually equal to ws dx vt vs, ws dx vs plus as, which is the same again. This one also holds wt dx vt plus at. Does everybody see that? That inequality holds as an equation, which means that f of x is actually not bigger than what you wrote here, but it's actually equal to, as well as this. Okay? That's it. What do you think? Is sufficiency easy or difficult?
In the sufficiency part, we will assume that these 3 holds.
Uh-huh. Yes, yes. You will assume that those 3 statements hold, and then you will show that w of n is equal to f of x, which is equal to alpha st. Okay? All right, work on it at home. It's good exercise for you. Property 4. The weighted diameter is defined by a single index, SS, or A is equal to AS, for some vertex index S, if and only if the f function evaluated at that vertex is equal to AS. So let's begin with necessity. So you assume Wn is equal to AS. Let's take an index P for which f of Vs equals. So let P be the index for which f of Vs is equal to Wp times the distance between P and S plus AP. So all I'm doing is I'm looking at the evaluation of the function at this point, at vertex Vp. F of x, or f of Vp, is the maximum of weighted distances to all vertices. One of them will realize the maximum, and that particular index is P, so that this index gives you the maximum. So this is greater or equal maybe I should write this as SP rather than PS, WIDSI plus AI for all I, okay? The maximizer of F. Now, if you recall property 2, this implies, property 2 implies Wn is equal to As by assumption that's greater or equal f of x. So in particular, f of Vs. So we have the following. Wn, which is equal to As, which is equal to Ws plus Wp divided by Ws plus Wp times As. I'm just multiplying As with 1, that's all. Which, when you open it up, becomes Ws As plus Wp As divided by Ws plus Wp. Now that one is less than or equal to Ws times f of Vs plus Wp As divided by Ws plus Wp. Well, over here, all we did is to replace As with f of Vs, and since f of Vs is greater or equal to As, then of course the inequality follows. Okay? So it follows from here. Now, if you continue, that last expression is equal to Ws Wp dsp plus Ws ap plus Wp as Ws plus Wp. Where did I get this from? Because I assumed P is that particular index for which f of Vs is equal to that. Okay? So, in place of f of Vs, we're simply putting this expression that you see here. I hope that's what it is, yeah? Ws times, yeah, Wp dsp plus Ws ap, yeah. It is that, okay? Which simplifies into dsp plus ap over Wp plus as over Ws. I'm just dividing everything by the product of Ws, Wp. That's all I'm doing, which is at the bottom we have 1 over Ws plus 1 over Wp. And that, of course, is your alpha Sp. But what do I know? I know alpha Sp is less than or equal to As. Where does that come from? That comes from the definition of W. W by assumption is equal to that, but W is the largest of the alpha ij, so you should have that, okay? So this inequality comes from here. The remaining stuff is simple linear manipulation, that's all. It's algebraic manipulation, not linear, algebraic manipulation. So what is my conclusion? The conclusion is straightforward. You've got, again, lower bound Wn, and you've got the upper bound Wn. When they are equal, all inequalities in between must hold as equalities. So everything is sandwiched. So when you have equalities, of course, the statement follows. F of S, Vs must equal to As. This one holds as equality. That's the one where I replaced As with that. So that's the conclusion. It must be an equation. The second part. Suppose f of Vs is equal to As. So until now we proved the necessity. Now we're talking about the sufficiency. This part is really simple. Under the assumption f of Vs is equal to As, property 2 simply tells you that f of x is bounded below by Wn, in particular by f of Vs. And by assumption f of Vs is equal to As. On the other hand, the definition of W implies As, that's alpha SS, the same as alpha SS. So Wn is greater or equal to that, which means Wn is bounded above and below by As. It's always the same proof technique. You've got equality. Simple manipulations, but you have to see, of course, where that leads to. Okay? After a while, you start seeing these things. Initially, they may look kind of all scattered around. Yeah. Yes.
Where did we prove the uniqueness of the point?
Okay. I didn't. What do you think? Where does that follow from? Think of this. We proved that f of Vp is less or equal f of x. And sorry, not Vp, Vs. And that's equal to that, okay? We proved this. Did we prove that? Well, actually, we did not prove that. We proved this and that. But because of the lower bound business, we also proved this. Okay, this is a byproduct. Now, if x is different from Vs, what do you think will happen? Let's just think about that. Well, f of x, which is the maximum of, well, you know the definition. F of x is greater or equal each of the terms in the maximum. In particular, it will be greater or equal how much? AS plus distance or WS dx Vs. This is positive. Yes, this is positive. So we're talking about AS plus some positive quantity, say delta. Okay? So the entire thing is greater than 0. So this thing is great. Sorry, this thing is greater than AS. Okay?
Assuming that weight of S is greater than 0.
Assuming where?
WS is greater.
Yes, yes. Yeah, I'm assuming that. All weights are positive. I'm assuming that. So because of this, the uniqueness follows. Okay? Good question. Yeah. So at the end of the proof, it's a good idea to actually write down that observation. In either case, the f function evaluated at Vs, it's equal to that, and is less or equal f of x for all x in the network. This is due to property number 2. F of x is bounded below, and you proved that f of x is equal to Wn. Okay? I'm just rewriting what we did already. Okay? Okay, we're sort of out of time, or maybe we are out of time. So I'll stop here. But next time, maybe if you remind me, I'm going to give you a small picture that actually tells you what's exactly going on with these things. Algebra doesn't tell the whole story. Pictures tell you a lot. Okay? All right, see you on Wednesday now.